after going through that Lewis derivation, we will go through detailed design procedure, which I have made it in a very simplified form. So one more thing, hard copy of this notes will not be given to you. You need to make your own notes, listen the video very carefully and make your notes, and probably during my regular session I will be quickly glancing through this particular slides, and again directly we will plunge into solving of the problems. So design procedure basically there are 8 steps, okay, in spur gear design. Of course these designs will be almost common in further like helical gear and then bevel gear and then worm gear. Of course some slight modification is there, but if you understand this particular spur gear design procedure, further it is going to be very easy for you. Okay, basically there are 8 steps. So as I mentioned in the previous video lecture, there are basically 3 criteria upon which the gear has to be designed. The first is static strength consideration, that is Lewis equation. The second is going to be dynamic condition, that is Buckingham's equation, and third one is going to be wear load condition. I think the same thing is repeated over here. The first one is static load design, second one is a check. I have written check for dynamic load and endurance limit. It is basically dynamic load consideration only, and then last one is going to be check for wear load. Under static load, so we have got various steps. So one by one I will read out here, and if possible you remember them 1 or 2 times if you write out. So it needs to be some just like some printed in your brain, so it is going to be cakewalk while solving the problem. And of course in the detail I will be narrating in further slides, and then we will go ahead. Step number 1 in static design only. Under that there are totally 5 steps. One by one I will read. Step number 1, in this particular step, in case if the material is not given in the problem, of course in the most of your academic learning or your question paper and all, passing examination view and all, so most of the times we do give the materials. You design the gear so and so, having a pinion material equal to so and gear material equal to so and so. But in most of your professional design, nobody will give you. You'd give me the design. Do you say that while buying any car, you give me the gearbox, gearbox made up of cast iron gears only to my car and all? You won't say. So it is a designer's responsibility to select the material. So under that purview, that is looking into your professional purview, I am just narrating this particular step. In case if the material is not given in the problem, you are free to assume. How to assume, what to assume, we will see in detailed procedure. And in the second step, assume minimum number of teeth on pinion. Okay, remember every time you have to assume a minimum number of teeth on pinion to avoid interference. So this I told. What is interference? Interference is basically coming in contact of involute part of one tooth profile with non-involute part of another tooth profile, which creates some sort of digging action and material removing wear and tear, and because of that there are possibilities of what you say failure. Okay, in that context you have to select minimum number of teeth to avoid interference, which I will be narrating. That is step number 2. And third step, you have to check the design criteria using Lewis equation form factor. Design criteria means what? You have to decide whether gear is weaker or pinion is weaker. How are you going to judge upon? There is something called as Lewis form factor. If you remember that constant terms I told, that is pi into y divided by something, no? So that constant, that capital Y I told before, capital Y is pi into small y, that small y is Lewis form factor. That multiplied multiplied by sigma d. What is sigma d? It is the strength of that particular body material. That is, if it is a gear, what is the material of the gear? That sigma d you have to take, multiply it by the Lewis form factor, and then find the product of that, whether that product of pinion is greater than gear or less than gear. So whichever is the less product, that material product is less, that is going to be the design criteria. In other words, if the product of pinion is smaller, it will be pinion which will be weaker. If the product of gear is smaller, it will be the gear which is going to be the design criteria. So that you will be doing in step number 3. Then further you will be calculating module using Lewis equation or Batch's equation. Remember, there are two. One is Lewis equation, another one is Batch equation. Lewis equation already we have that Wilfred Lewis we have seen in the previous video. It is same actually. Okay, so or one more is there, Batch equation, which I am going to narrate. Okay, then again that is step number 4. The last step in static design is a check for percentage variation and stress induced. What do you mean by percentage variation? There is one ratio, that is a difference between RPM and diameter to the RPM, that has to be less than or equal to 1%. So what happens sometime if there is a mismatch, so that one driver is going to be rotating faster or driven is going to be rotating slower, so there will not be proper proportion, that is law of gearing will not be met. In that context you have to verify. Being a designer, of course most of the books will not tell this, but you being a professional, this thing you have to do this properly. And again, whatever the module you have found out in the previous step, that you have to verify, because while solving that Lewis equation, certain assumptions you will be making, because most of the data will not be known to you. Under that circumstance, you make an assumption. After that, after calculating the module, all the data you will be exactly finding out, and then check the induced stress using same Lewis equation only, which I will be narrating in detailed design. So this is going to be static load design. Coming to the dynamic load and endurance, you have step number 6, in which you will be using that Buckingham equation, which I will be narrating in detail. So using that Buckingham's equation, you will be finding or checking the dynamic load. And again in the same step, endurance limit. Endurance, what is that? Whenever the load is not static, when it changes with respect to time, it is not the static strength we consider the endurance limit. Okay, generally remember that. I think in your cyclic loading of your machine design learning, you have come across that. I think you have a Goodman criteria, Soderberg criteria, and all those particularly that endurance limit and all. Okay, when the load changes, right? So that you will be doing. And again in the same dynamic only step number 7 will be again procedure has to be followed for checking the endurance limit. Okay, so these are going to be in that part, dynamic part. And lastly it is going to be wear load. And again remember, it is the last step, which is very simple, and there is no ambiguity. Ambiguity means in the previous up to step number 7, whichever is the weaker part, either it is a pinion or gear, for that only you will be doing the design check for this particular static load and dynamic load. What does that mean? If it is a pinion is weaker, you will be doing all the procedures pertaining to pinion only, that is N1, R1 or force FT1 and all that kind. But whereas in wear load, irrespective of design criteria, you will be doing wear load test only for pinion, irrespective of design. If at all design criteria is not pinion, even after you will be doing this wear load test for pinion only, which I will be narrating in depth during subsequent. And again we will go to step that particular first one, that design procedure, the static. I will read out this which is self-explanatory, and if required I'll just try to narrate you. Okay, so if material of gear is not given, it may not be gear or it may be pinion as well. If it is not given in the problem, then choose the same arbitrarily. Arbitrarily means with some thumb rule. Okay, it is preferred to choose both gear and pinion material as same, so that step number 3 can be eliminated. Okay, it can be eliminated in the sense, so no need of verifying that particular step number 3. That step number 3 is, if you just look into that first slide, that is sigma d into y is there, no, so no need of doing it. Is all the time which is going to be inferior means it is a pinion. Of course, only after solving the problem you will come to know, but as of now you consider if material is not given means you are lucky, so you can assume both are made up of same material and you can just proceed. Or if it is not given, there is one more guideline, probably this may be of very useful during your profession. So they have given very this thing elaborately, that is you have to decide the type of material depending upon what is the quantum of power to be transmitted in that particular application. Like if power to be transmitted is less than 200 watts or 0.2 kilowatt, and if it is a DC application, DC means direct current application, use non-metallic gears such as Hilum. Hilum is one type of material. It is actually some artificial material. Okay, so it is being used. Just Google search that, you will come to know what are the constituents and all. Okay, or if it, you can also make use of composite material. Lot of composite materials are available nowadays, so you can go through that and then you can adopt in your design, or even you can go for as cheap as plastic ones or some other. Okay, depending upon the availability and again working conditions and again cost, all those parameters you do consider and then select. Why you have to select this? Because as the force to be transmitted in these cases will be of less magnitude. That means whatever the power to be transmitted, it is very less. 200 watts is just nothing. For example, if you in your electronic goods, if you take a tape recorder, that tape recorder, of course, and I think most of you may not have come across, that is a tape, actually magnetic tape, which will be slowly rotating. Now it is all a CD drive basically. So CD drive, whenever you put the CD in your laptop or desktop, so CD will rotate. Of course, the CD technology is also outdated nowadays because you have all pen drives and all where there is no driving, this thing is there. But of course you have some fans in the laptop, desktop also you have the fans. Just open them for your what you say curiosity. You notice that all those are made up of plastic gears, they are not metallic. In addition to that, if you see any camera, that zooming will be there, no, lens making out and then taking inside for the clear image. So that automatic cameras and even manual camera, there also small gears are there. They are all made up of plastic gears only. That is, if the power to be transmitted is less, go for non-metallic gears. That is thumb rule number 1. And second one, if power to be transmitted is between the range of 200 watts to 7 kilowatt, okay, then use cast iron gear combination or soft gear combination without heat treatment, preferably of low carbon steel. This is a low carbon steel is less than 0.3% carbon, which wherein no need of doing any heat treatment. And reason is, again, it is up to 7 kilowatt, no need of this thing any, because again if you do heat treatment or if you select any high strength material, cost will be beyond your this thing, and it is not advisable also. In that context, you follow the step number 2 recommended for material selection depending upon power. Again, remember, of course, okay, power means again it is in turn that material selection and all is also economic this thing, so they are one and the same, but thumb rule is on power you have to decide upon. And the last one is, if power to be transmitted is greater than 7 kilowatt, then you go for heat treated alloy steels. Okay, again that I will just show you from where all you have to select. Okay, so for above 3 steps, choose material from the table of your design data book, Mahadevan and Balveer Reddy, table 12.7, page 234. So the number table what I am referring is, I think, recent edition, that edition number fourth edition. Okay, it may be different table number, page number. If you have any other than this particular edition, please check that. Okay, so you have to refer that table and then take that. Okay, here sigma d is given. Okay, I think I had told it elaborately that sigma d is actually sigma bending we have taken during derivation of that equation. It is the same as the strength of that. Sigma d is the static strength of the material, or allowable strength, static strength of the material. And in the same table you have BHN. BHN refers to core BHN. Core BHN means what? You have the core inside and then you have the surface of the gear outside. Okay, so core is inside. Inside is called core. The BHN, whatever is referred to there, it is going to be the core BHN. So this is design step number 1. Further, you have step number 2, which I am again reading out and then trying to narrate to the best possible. In this step number 2, you have to select minimum number of teeth on pinion. Remember, always on the pinion you have to make an assumption. Again, this assumption has to be done in case if the number of teeth is not given. Only if it is given, you have to stick on to that and solve the problem. So these are the general guidelines in the worst condition of data. Okay, remember that. So for that you have to refer table 12.4b, page 230. There are 3 columns. Basically you read out, they are self-explanatory, that rack and pinion and intermittent, something like that. In the third, for continuous motion, it is there. So you have to refer, because this gear pair, it is a continuous motion, it is not an intermittent or nor a rack application. Okay, you have to refer that. And the procedure to be followed only if Z1 is not given in the problem. That is what already I have told. If tooth system, that is the tooth profile, is not given in the problem. Suppose, I think I told this, that there are 2 types of tooth profile. Of course, there are 3 base in depth, to be precise. 3 means 20 degree full depth and 20 degree stub tooth, and another one is 14.5 degree. Okay, if nothing is given in the problem, you are free to make an assumption either 20 degree or 14.5 degree. Okay, so this you have to follow. Okay, and again there is one more note. This procedure of assumption of minimum number of teeth should not be done if center distance between pinion and gear, okay, gear, I think there is some typo, gear is given in the problem, then do not assume Z1. Omit this step. Which step? The above step has to be omitted. Why it has to be omitted? The clarification I have given. Basically, what is that module? Module equal to D by Z. D is the pitch circle diameter of the gear, Z is the number of teeth. Okay, so if you make an assumption, what happens? This Z, if you are making an assumption, D is already given. How it is given? It is given in terms of center distance. What is center distance? D1 plus D2 divided by 2. It is already given. You are making an assumption of this. Then what happens? This module will automatically get fixed up. Fixed up means there is no need of any estimation. It will automatically set. You may get a surprise, sir. What is the problem if that is the case? That is not the this thing procedure. It has to be estimated. It should not get adjusted itself. It has to be estimated. So do not make assumption of minimum number of teeth on pinion to avoid interference in case center distance is given. Then what to do in that case? You have to use, I told one more, that thumb rule, batch equation. You have to use referring equation 12.8, page number 205 to estimate module. In that, if you just look into that module equal to 0.88 into cube root of I think that equation I have given in the next this thing step. Okay, so there you will come to know that is mt divided by k2 k into z. The mt is the torque, k2 is strength coefficient factor, and small k is width factor, that is b by m. Of course, I am all those things I am going to narrate now. And again z is corresponding, whichever is the design. If it is a pinion, you substitute corresponding to that particular z if it is given in the problem. If not given, again that has to be replaced by diameter and module only, because m equal to d by z or z equal to d by m. So you solve that equation to find out the corresponding module. This is going to be step number 2. And in the step number 3, what you have to do? In the step number 3, design should be carried for weaker component. I think I told this. If you make an assumption of both when material is not given, if you make an assumption of both gear and pinion as the same material, now you can skip this basically. But since if it is given, then again you can't skip. Now what you have to do? You have to declare which is going to be the weaker. I think elaborately I had told. Again I'll read it out, so it is self-explanatory. Okay, in this case it should be for pinion or for the gear, whichever is weaker in strength. This is judged by comparing their respective products of sigma d into y. What do you mean by that? Sigma d into y of pinion, here I have written sigma p means pinion and g means gear. So you have to consider the corresponding that y and then sigma d, that strength, and then find out smaller the product amongst these will be the design criteria. Remember that. Okay, further, if it is gear, you have to substitute all parameters pertaining to gear only, that is d2, n2 and all. If it is pinion, you have to substitute n1, d1, all those corresponding parameters. Okay, and again here sigma d, it is most of the time repetitive. You may get irritated because this I told sigma d is static allowable strength of component. Refer table 12.7 page 234, which I have mentioned in the previous slide also. Here also you have to take same value, and small y is a Lewis form factor. For this there are multiple equations, 12.5c to 12.5e on page number 204. Okay, that means you have for 14.5 degree involute, 20 degree involute and 20 degree stub tooth. There also there is a Z is there. So while solving the problem I will tell. So what you have to do when you are taking the pinion, that Z you have to substitute Z1. If it is a gear you are finding that Y, you have to substitute Z2 correspondingly and then try to find out that. Okay, and if both pinion and gear are made up of same material, then this step can be omitted with the conclusion of a pinion as weaker material. This again I have told, we will realize this when we solve the problem. Then we next slide, where step number 4, it is a module calculation. Okay, so module calculation means what? You have to find out the module. I think here very detail I have given. So calculate module using equation number 12.5, page number 204. I think just one small this thing. Yeah, it is correct only. In your data book, what they have given 12.5b, I think it is small b, not capital B. Anyway, it is page number 204. I have mentioned cube root, but whereas he has given inside the bracket of entire that 2mt divided by sigma d cv m y z to the power 1 by 3, both are one and the same. It is cube root only, wherein mt is a transmitted torque. Remember, it is, I think there is some problem, typo. It is a capital in Newton, okay, per not per, I'll just Newton millimeter, sorry. So it is Newton dash millimeter. I think there is some typo, Newton millimeter, make the correction. Okay, and then there is one more. If service factor is given in the problem, then multiply that same to mt. What is that service factor? Basically you know that sometimes that inertia factor and all those some unaccounted things are going to come, that has to be taken into consideration. Service factor is basically, you know this, generally it will be given in the problem, okay, which will be, I told in the previous, it is greater than 1. If it is not been given, you simply take it as 1 or discard that. If it is given, then you have to remember that, multiply that to mt and then substitute that particular mt multiplied by cs in this expression. Cs is maximum torque divided by rated torque. Okay, so while solving the problem, we will see that what is that. Basically generally CS, as I told, it is directly given. If not given, they will give the maximum torque and rated torque. Through that you have to find out this. And again sigma d, again repetition, allowable stress of the corresponding material, whichever is the design criteria, that material you have to take in megapascal. For that again repetition here, table 12.7 page number 234. And K, capital K, it is a size factor, which again I narrated that it is B by by m, small b is the phase width, m is the module, it is unitless, and that value from the data book equation 12.5 f page 205 you refer, it says that this particular ratio b by m or k, it has to be between 9.5 to 12.5. that means either if it is given, well, otherwise you have got a free to make an assumption 9.5, 9.55, 9.56, 58 or 10 or 11 or 11.5, 12, 12.49 also you can take. Okay, so as far as possible do assume somewhere near 10, because in case if it is not safe, you will have some what you say iterative procedure to make the alterations till that gear is safe, which I am going to subsequently tell upon. Okay, and then again one more, that capital Y in this expression, that is capital Y is there, so that is capital Y is pi into small y, that is Lewis form factor, which I have narrated in the previous slide, and Z is a number of teeth on weaker part, which is a design criteria from step number 3. that means they will not be giving, they will give simply Z. You have to decide whether Z1 has to be taken or Z2 has to be taken. How we can take that? Whichever is the design criteria. If it is a pinion, in place of Z, substitute Z1. If it is a gear, design criteria, in place of Z, you substitute Z2. Okay, and the next one is going to be CV, that is velocity factor. Okay, for that refer equation 12.5a to 12.6d page 205. So there are multiple equations, that is up to 8 meters per second bars formula, and then up to 13 meters per second, 20 meters per second, and more than 20 meters per second. And for non-metallic gears, everything is given CV value 12.6 A, B, C, D up to E. Okay, I think 12.6, I think it is 12.6 only, I think 12.6a, there is some again typo mistake, it is not 12.5, it is 12.6a. please make a correction, again page number is correct, it is 205. Okay, if velocity is unknown, that means in the in some of the cases it is so this thing that you will not be knowing the velocity. Under that condition you choose CV somewhere around 0.5. again this is a thumb rule. This is thumb rule. If nothing is given, so you take around 0.5, because you will come to know that CV value will be varying somewhere around 0.5 to 0.8, 0.9, something like that. Under that context, I am telling you can take 0.5. And after finding the module, so what you have to do, you have to estimate the exact value of CV and check for applied or induced stresses. Okay, in fact I am clubbing it, this check has to be done in step number 5. so actually we are in step number 4, just for the continuity I have told. So this checking and percentage variation has to be done in next step number 5, wherein all your static strength consideration will end. Okay, and again Lewis equation 12.5b can be used for finding that particular I don't know why I have substituted for CV you need to have, I think induced stress. For induced stress, again that module whatever you have found out now, same equation has to be used. That is actually you have a sigma d over here in spite of in place of sigma d. What you have to do, you have to find the induced stress using same expression. Okay, that module was cube root, so that m cube has come over here, and that value has to be less than or equal to sigma d. Remember that sigma d is a strength, so this is the induced. So CV earlier you have assumed, now after finding the module you find out the exact CV and try to substitute in this expression, and then check whether it is less than or not. If not, again what you have to do, you have to reiterate. Reiterate means you go on changing the value. Don't immediately jump for going for the higher module. You have to go for increase face width or some other parameter you have to do, which in the subsequent step I am going to tell. Okay, and where sigma I is induced stress. Okay, Okay, the cutters are standard actually, as I mentioned. So you have to select for that. If it is large difference is there, you have to go for second choice. Suppose that is also not possible, means last option is choice number 3. Okay, so this you have to practice. And if that center distance is given, again I told you go for not that, do not make an assumption of minimum number of tooth on the pinion. So what you have to do, you have to go for using batch equation, which I am narrating. That batch equation m equal to 0.88 cube root of mt k2 k into z, which is given 12.8 equation, page number 205. Okay, so what is that mt? Same torque. K2 is actually strength factor. They have given, refer that data book. Please keep a data book side by you while you are listening to this audio, audio module of this video, so that it will be clear for you. Okay, you can pause, make your own notes, and then make comfortable. Okay, that is K2 is that strength factor. What is K? K is the width factor. B by M, whatever you have done, no, in the previous, the same thing. And Z is whatever is the design criteria, Z of that only you have to substitute. That means either it is gear or it is a pinion. Depending upon that, you have to substitute Z1 if it is a design criteria is pinion, or Z2 if the design criteria is gear. Suppose Z is not known, then what you have to do, that Z has to be replaced by, again say module equal to D by Z is there, no? So Z equal to D by M you have to substitute, and again D is the center distance. If it is given D1 plus D2, you have to determine what is D and what is D2, and through that you have to solve for M and then find out the module. That is going to be in this particular. With the next step I will just stop and I will make one more, because it will be lengthier for you also, it is difficult, and for me also again difficult. Then this is going to be the last step, that is a check for percentage variation and induced stresses. Okay, induced stresses I have already explained in the previous step. Only percentage variation I will tell. So this formula is not available in your data book. Remember, I told this, it is also very important, because if one rotates faster, another rotates slower, again it is going to be problem. Under that constant, under that context, percentage variation is ratio of d1 by d2 minus n1 by n2. I have made minus here, again I have written with a hand this thing. Okay, scribbling. You take a difference basically. Do not again, if d1 by d2 is smaller than n1 by n2, you will get a negative this thing. So variation cannot be negative. It is just a difference of d1 by d2 difference n1 by n2. Okay, you take the difference of ratio and do not consider the sign. That is, if it comes negative, it is of no meaning. That is why I think that differences I could not able to insert that equation. That is the reason I have written with the hand this thing, divided by n1 by n2 into 100. This has to be less than 1%. That is 1 divided by 100, 0.00, 0.01, 0.01. Okay, so 10 is I think 0.1, yeah, 0.01 it has to be. So that variation you have to check. If above condition is not satisfied, then again same iteration what is being told previously. Iteration means you change the module or you change the diameter, okay, until the above condition is satisfied. So for induced stress check, that is check for induced stress, refer the last step of that step number 4, whatever I have narrated. So what I will do, I will stop my video here. It is already 32 minutes. So in the next further, that is dynamic and wear, I will do it in the part number 3.